So we're going to start lecture 4 with a discussion. Well, lecture 4 is going to be focused on effective actions. Now, it's going to be a little bit of a detour from the plan I had. I had at the beginning for this course. Initially, what I wanted to do was I wanted to do a renormalization group and then come back to effective actions, The reason being that effective actions is like a subfield that's often discussed as background field methods. So we're going to see that, what the content of that is. But I realized that it's sort of inevitable to talk about, like if I explain the background field method a little bit earlier, then I can do a better job of presenting RG. So I've moved stuff a little bit around, okay? So today we're going to discuss a little bit of that. I'll give a summary of what we're going to discuss today in a bit, so that you're not lost. All right, so review of what we talked about in lecture 3. Are there any questions from the previous lecture? Well, as we go along, if there are questions, just answer. So in the previous lecture, we discussed renormalized perturbation theory. The principle was pretty simple. You start with bare fields. These are the things that you put in the Lagrangian. Define renormalized fields with a bunch of renormalization coefficients, parameters. We call these DAs. This is just some arbitrary constant we put in there. We call them the wave function renormalization. Then you take the bare Lagrangian, written in terms of bare couplings and bare fields, and write it in terms of normalized Lagrangian, where both of the field and the couplings are normalized, plus counterterms. Counterterm is whatever is this minus this, right? So these are counterterms in coupling that we organize as a function of phi of r and a bunch of couplings, some values delta of a. What we're going to do, so far it's just like shuffling things around. What's called renormalized perturbation theory is taking this action and treating it, doing Feynman path integrals or perturbation theory for their renormalized fields, treating these counterterms as interactions and just including them in your Feynman diagrams, right? So there will be new Feynman diagrams due to the counterterms. This is what renormalized perturbation theory is, and we worked at 2 examples at one loop, scalar field theory and QED. Are there any questions about the calculations we did over there? So in scalar field theory, there were 2 things that we need to correct at one loop. There was the mass, self-energy, right? Mass that had to be renormalized. We discussed that. There was basically one diagram that contributes to it. That's one loop. It's this diagram, right? And for QED at one loop, and then there is a vertex, right? At one loop, we had the this plus the other 2 channels, the other 2 way of contracting them, right? We did these 2 calculations for scalar field theory. We normalized at one loop using local counterterms. We did QED. For QED, we had 3 diagrams we had to worry about. The propagator of photon, right? That's the vacuum polarization. The propagator of fermion, that's the self-energy of fermion, and the vertex, right? The coupling of electron and photon. And we did that at one loop. All right. Then we commented on symmetries, the interplay between symmetries and renormalization. This is a longer story, but it's for the purpose of this course, we're just going to present it in the context of QED as an example, right? Well, we started that. I might come back to this in non-abelian gauge theories. I will come back to it. We said that every time we have symmetries, classically, we have Noether theorem. We have Noether currents. So we have conserved currents. So these are equations of this form. These are classical equations, right? That we found by shifting the field variables, right? We did find equations of motion by shifting the action, by shifting the field variables in the action as well. So in equations of motion, what we found was that there was an equation del S del phi was equal to 0. This is a classical equation. Then we discussed in the quantum world, this is no phi becomes an operator So if you take the equations of motion viewed as an operator, it's no longer equal to zero. The expectation value of this thing, time ordered next to any other operator, will only include contact terms, and this is what we call Schrödinger-Dyson equations, and this is a non-perturbative way of repackaging quantum field theory. Similarly, when you have this classical equation in the presence of conserved currents, the quantum version of it has a very similar flavor. It just says that if you take del mu of a correlation function of time ordered J mu next to a bunch of other operators, right? This is only contact terms. Is it clear what I mean by contact terms? It's non-zero only when things overlap. So it's proportional. If you have 2-point insertions, it's proportional to Dirac delta function, but it could depend on derivatives of Dirac delta function, right? All right. So in QED, we give an explicit example of this when a fermion is coupled to a current, right? And in this case, we are looking at a 3-point function of J and psi bar, right? And we saw that the contact terms of interest are just 2-point function of psi bar with Dirac delta function when X is on X1 or X2 with minus Q and Q because of the particle antipode. And the point, so now this is so far just what Ward identities are. They are quantum consequences of conservation laws, right? That's what Ward identities are. Now, how does it interact with not renormalization? The way it interacts is that just the same way that Schrödinger-Dyson equations related higher point function to lower point functions up to contact terms, Ward identities relate higher point function to lower point functions. This means that they relate the divergences in higher point function to lower point functions, and that's important because we are doing dimensional in our normalization group. The point is to make sure all the infinities are canceled in arbitrary point functions, right? So we said that Ward identities are non-perturbative results, right? They are like Schrödinger-Dyson. They're non-perturbative. In Fourier space, we wrote it this way. It's basically this expression, Fourier transform, right? So this is the vertex. This is the full vertex, P1, P2, and Q. So Q mu, M mu takes this form. These are the Fourier transform of these guys. And this is called the Ward-Takahashi identity. And often we discuss this in the context, in the limit of Q going to 0, the soft photon, emission of soft photon. And in that limit, that just tells you that this guy, conservation law tells you that P1 slash is P2 slash plus Q slash, right? So you expand this in Taylor expansion, you bring out the Q mu that will cancel this, and you learn that T mu of 0 PP is the derivative of P with respect to S minus 1. And of course, because this is P slash and this is P mu, this derivative is proportional to gamma of mu. Oops. Yeah, gamma of mu, and that should ring a bell, right? So in the classical limit, in the true level, that is the 0th order contribution. Then we concluded that Ward identities in QED at true level is just energy conservation. It's guaranteed by energy conservation. At higher loops, I said that there is this super duper fancy theorem, BPHZ, and its related results. I don't really know which result is the one to point out, but they guarantee that in renormalizable theories, local counterterms can cancel divergences, to all orders in perturbation. So if you take an arbitrary quantum field theory that you know is renormalizable, then based on the definition of renormalizable that we have, then you pick to do this to 23 loops, right? There should exist a finite number of counter terms that they all look like local terms in the action, and they will cancel divergences. Why do I keep insisting on locality of counter terms? What physical consequences are there for the cases where the counter terms are non-local? the terms in the counter terms are non-local. Remember that the counter terms, the counter term Lagrangian was the Baire Lagrangian minus your normalized one. So you know that the Baire Lagrangian is local, right? So the only way to conclude what you conclude is that, well, this is the condition that the renormalized Lagrangian is renormalized. Is local, sorry, is local, which is desirable because of locality and everything. So we want the field to be renormalized by an amount, right? The wave function can get renormalized, but local expressions should remain local. All right. Is that clear? Any questions? All right, so this is a summary of what we did in lecture 3. What are we going to talk about today? First, First, we are going to go over a couple of two-loop calculations in lambda phi 4 theory to just make sure that you've seen it all, and to just see the structure and the mathematical tricks, because this structure just generalizes. It gets more awful, but you see the picture, you get the picture. There are a whole bunch of things, and we will observe precisely how local counterterms cancel all divergences at two loops. Of course, I will not have time to do all the algebra on the board, but I'll give you a bunch of expressions, and your homework will fill in between. We do this before discussing. Before the next natural discussion is just talking about renormalization grooved flow, which is, so we renormalize the theory. We saw that we could renormalize the theory at the renormalization scale. We also had an evidence, we saw in examples where the couplings were renormalized dependent scale. So as we change the scale, the couplings run. The dependence of the couplings on scale is called renormalization grooved flow. So we're gonna, at some point very soon, zoom out and discuss that at high level. What is renormalization grooved flow? How to think about it non-perturbatively, just on the path integral. But before doing that, we're going to do a little bit of a detour, this lecture and the next lecture, discussing something that's called background field methods. The logic being that once I explain this, then I'll introduce a tool here called effective action that I'm going to use over there in our Gflow to explain things a little bit better. Is the logic clear? So there's a little bit of disconnect between this lecture, part 1 and part 2. I couldn't get it done at the end of one lecture. So here we go. In part 2 of today's lecture, we're going to start the discussion of background field methods, and the punchline, the key idea is going to be introducing a generating functional we're going to call effective action. It's a general generating functional for 1PI diagrams. I'll try to motivate this even better. So by now you know 3 generating functional. By now you know 2 generating functional. Partition function. Sorry, I'm sorry, partition function. We call this something. Well, we call Z of J. What is that the generating function of? Endpoint functions. Then we had W of J, which was minus I log of Z of J. What was this generating functional of? Connected diagrams, right? Then we talked about connected diagrams, we talked about all point functions. We also introduced 1PI, right? One particle reducible diagrams. So now we're going to introduce some objects, some functional, who's the generating functional for 1PI diagrams. And it will have the flavor of an action, but it will include all quantum corrections. This is all you need to know about effective actions for now as a way of motivating. So it's like it's something that you use as an action principle. It's a functional, you vary, but what comes out of it is 1PI stuff, which includes all quantum corrections. Good? All right, so scalar self-energy at 2 loops. So this bit is going to get a little bit technical, but I want to walk you guys through it. It's going to be a little bit painful, hopefully not too painful. So at 1 loop, there are 2 diagrams that contribute to 1PI. So this is 1PI scalar propagator. At one loop we had this. This is order lambda r, order lambda r because there's just one vertex. At two loop there are these two, right? There's like two bubbles on top of each other, and then there's a line and a bubble going through it, right? So these are the two loops. They're order lambda r squared because there are two vertices. All right, so let's pick the first one, the two bubbles. So there's Q, yeah, so let's say this is K that, let's just forget about the external legs and let's work with the amputated thing. So K comes in, P goes this way, right? And this is K. All right. We have two, so that what does the diagram look like? It's 1/4 here. This is coming from the symmetry factor. What's the symmetry? You have two loops. You could flip this guy like this, flip this guy like this. That's Z2 times Z2, factor of 4, right? You have minus I lambda r squared, which is coming from these two vertices. You see my, okay. Then you have an integral over momentum P, integral over momentum K. They're both bosonic, so they come with plus ones. You have the propagator for P. There's one propagator, I over P squared minus MR squared. Remember that we're doing perturbation theory, renormalized perturbation theory, so this is MR squared, right? And then there are two propagators, right? With MR squared. I think I've always switched to minus one plus one minus minus one. I'm so sorry. My whole metric convention is all over the place. Sorry about that. But if I teach this again, I'll make sure my metric convention is fixed. All right, so this is what comes with the power of 2 because there are two propagators. Good. So to be able to keep track of these integrals, it's helpful to define this thing called K1 and K2. What this is it's Kn of M squared is defined to be an integral over the propagator to the power of n over p, right? So this is, I usually simplify this integral as write as integral over p. So this is the d-dimensional integral over p, and I over p squared minus m squared to the power of n. This is called Kn of m squared. It's an integral that's going to appear over and over again. So it's pretty clear that this is the K1 of mr squared, and this is the K2 of mr squared, and minus I lambda r squared. Wait a second. Am I missing factors here? Yeah, maybe there's a coefficient here. Right? Maybe not. Maybe there is, yeah. All right, so the point being that it's proportional with K1 and K2. What we did when we did the one loop calculation, this diagram, right? We basically did the integral of K1. That's what we did, right? We did the K1 integral and we found that there was a 1 over epsilon pole in it and dim reg. If you do the integral and for K2, you also find 1 over epsilon divergence in it. So the divergence of K1, K2, the divergence of this diagram is order 1 over epsilon squared in dim reg. Epsilon is 4 minus epsilon, right? It's just near 4 dimensions to recall. So it's not a simple pole. That's the whole point. It's not a simple pole. Now you might find that confusing. Dim reg, remember we motivated dim reg because we wanted to keep we wanted to keep gauging variance for QED, right? And we needed it because the momentum cutoff was not respecting gauging variance, was not respecting word identities. We motivated that way. We could use it for like scalar field theory for all sorts of field theories, but motivated that way. In the case of scalar field theory, sometimes thinking in terms of the momentum sharp momentum cutoff gives you extra intuition because this is less intuitive, at least for me. So if you have an integral of this type that we had, right? Where do the divergences come from? They come by dimension counting. This is p to the power of 4, integral of dp4, and this is at large p. You want to focus on large p squared, right? So this is like 1 over p squared and d4 of p. So this bit grows like lambda squared. This is like d4 of k, but then 1 over K4. So this grows like log, right? And I say lambda squared because if you remember, we went to Euclidean space to do these integrals, right? We did the Wick rotation. That was one of the things that we did, right? And then yeah. So this diagram that we're discussing diverges like lambda squared log lambda squared. And of course, inside the log, you should have something dimensionless. So you can just put by hand mr squared, but it will come out correct. All right. Okay, so that's the structure of the divergence here. Now, if you have it, but more general, if you have a diagram at n loop, now you can do the counting very, very easily, right? This diagram will be proportional. So this is the n bubble diagram. It's an n loop term that appears in propagator. It will have lambda to the power of n because it has n vertices. It will depend on lambda 2. It's not hard to convince yourself because as you're doing this, as you're writing these Legos, you learn that basically for this n bubble diagram, you have one of these integrals that diverges like lambda 2, and all the other integrals diverge like log. So you end up with log to the power of n minus 1 at n loop. So that's one diagram. Another diagram that's an n loop diagram. You could add these bubbles to your vertex. Normalization of vertex, and it's just a pretty quick to argue that this is, I leave it for you guys to figure out, but it's pretty simple. You could see here, this goes like lambda to the power of n plus 1 because of n plus 1 vertices, and the log of lambda, the whole thing to the power of n. Right? So recall the principle of renormalization. What we wanted to do was we wanted to make sure, so we are canceling the coefficient of all the power laws, divergent terms, right? We want to make sure anything that's not power law divergent also cancels. At one loop, we're canceling all the logs lambda terms by hand. Well, we actually canceled them. As we go to higher loops, the technicality is that log of lambda to higher powers appear, and you have to make sure that they cancel. Now, there's this formal theorem that ensures that they will cancel, but let's see how it works in the case of scalar field. So for this bubble diagram, this particular diagram, the two bubbles on top of, sorry, not two bubbles. This diagram, whatever it's called, I don't know, I don't have a name for it. There's a counter term you can write down. The counter term is this, right? It's just based on, I'm not doing anything but Feynman diagrams for my initial Lagrangian, right? The renormalized Lagrangian. So what is this counter term? This counter term has basically, there's a p propagator here, there's a p propagator here, so 1 I over p squared to the power of 2. There are two of such propagators. This is that vertex, the counter term associated with it, and then there's an integral over p, and here is the only vertex we have, right? Okay, so you play around with this. This is just you do simple dimension counting. You can expand them, and you find K1 here and K2 here. Is it clear why this is K1 and K2? Because this is power of P2. This is 1 over P4 in the definition of P. So you just add to this P2. So you add and subtract the term minus MR2 del Z plus MR2 del Z, right? Now, these two together cancel one of these powers. That will give you a K1, right? And these two together will conspire to K2. Good. All right. So now this is supposed to be a two-loop calculation, right? K1 is order 1 over epsilon. K2 is order 1 over epsilon in dim-rec. So you know that delta Z and delta M's, you only need their 1 over epsilon, them at level 1 over epsilon, right? That is precisely what we calculated from the one loop answer. So from the one loop answer, you know that del Z order 1 over epsilon is 0, and we also computed del M of 1. So just plug that, the fact that del Z is 0, these two terms go away, you end up with this, right? Okay, that's good. You just add these two terms, you find that the two-loop answer, the two-loop diagram plus the counter term is minus I lambda R squared K2 times the parentheses. But this, what's in parentheses is was precisely what we canceled in the one-loop normalization. So you get 0. the proof of this theorem, if you want to prove that renormalization can be done systematically, is sort of like intuitively telling you that as you go to higher loops, right, there will be all sorts of diagrams. But when you expand them and write them and add all the counterterms, this becomes a whole bunch of expressions with coefficients that you have canceled out in lower order normalization. So it has to have this iteration. It has to be iterative. But we check that this is correct. This is a fact. All right, is it clear? So let's do a couple of more diagrams. So we said that there is another diagram that contributes to the 2-point function, right? So it's Q, Q, P, K, and this is Q minus K minus P. So this is the one propagator for the middle one, propagator for the bottom, propagator for the top, and you have to integrate over K and P. These are D4, K, D4, P, but I'm just writing them as this way. And this is the coefficient, and this is the symmetry, right? Hopefully, we could reproduce these. All right. So first thing that you notice is that you could do the integral over P. Let's focus on integral over P first, right? Why do I do it this way? Because the goal that I have is to write the true loop answer as something whose coefficient is the one. So I'm going to do one of the integrals first, right? So I'm going to try to do the integral over, which one do I try to do? P first. So the P dependent terms are A and C, right? So here, if you recall, the way we did this is we introduced Feynman parameters for 1 over AC. It came at the cost of introducing a new variable x from 0 and 1, and then we defined the sigma x, which was shifted, all of that song and dance. I'm not going to redo it, but this is the correct expression, right? So you have this expression, this, and this. You go back to your old notes, and you find that in DimReg, we calculated this guy. And in DimReg, this K2 thing was minus 1 over 16 pi, 4 pi over zeta of x of k and q to the power of epsilon over 2, gamma function of epsilon over 2. What you need to understand from this expression, what you need to focus on is that now in this new integral, you have 1 over, b, right? You have 1 over b and 1 over c of x, because c of x is q minus k squared minus, it basically looks like this kind of type of structure. 1 over something, which looks like this, right? To power of epsilon over 2. So what you would like to do is you would like to generalize your Feynman parameters to something like this. A to the power of epsilon 1, a to the power, or some arbitrary n and m, where n and m are real but not necessarily integer, right? And that's what we're going to do next. So there is this analytic expression you could use. I suggest that you guys use it. That 1 over a to the power of m, b to the power of n can be expanded this way in terms of gamma functions. And what's neat about this is that for m and n real, you could use these expressions. All right. So now, what does this buy us? Of course, we're doing Feynman parameters adds another variable, another integral that I'm going to call w from 0 to 1, right? There's a whole bunch of these gamma function stuff that I brought out. There's w to the power of epsilon over 2 minus 1, and this is the denominator, right? Which is how now this now has this funky power 1 plus epsilon over 2 because it's m plus n, right? Good. All right. What was the rest of it? So this is where I probably lost your, yeah. Yeah.
Here we are plugging in the one loop values of the deltas.
Yes.
But like, so so we write these deltas as a particular expansion in non-terms. So,
yes.
So shouldn't there be a term which includes delta, tau, or whatever, but with the, like, the second,
Oh, you're asking, because we're at two loop, so here's delta of z, for example. Let's expand it in the following way, order, well, sorry, how do I want to do it? Yeah, delta z1 lambda plus lambda squared delta z2, right, and so on and so forth, right, and then this would be a two loop thing. You're asking that, is there gonna be a two loop contribution of this type? Well, to this diagram, this is the only counter term that contributes. I'll give you an example of a setup where you have a counter term of that type.
I would like to count the power contribution. It's like, oh, is it just that?
So, okay, very good. The principle is like, you have to go back to the principle. You had this action, you just expand it and treat counter terms as interactions. So you draw all the diagrams you can, and you just have to just add them up, right? So you see, you in principle have to always assume a term like this. But if you don't need it, if you can cancel the divergences without, you set this term to zero. Right? That would be a special case. We'll see that in this scalar field theory, we'll need it. Not to cancel this divergence, but to cancel another divergence. Good. All right, here by now I've probably exhausted your patience, but let me just remind you quickly how we did the rest of the integral, right? So this is this integral. The next was we did Wick rotation, right? So we went to Euclidean momentum. We defined this shifted momenta L, if you recall, where we repackaged this whole thing and as a new variable, and then the next step would be a change of variables that allows us to do the integral. But the point here is that now the structure of this is again similar to before. So mr squared minus something times L squared. L squared is the thing that is the momentum that runs in the loop, right? So it has the L squared plus junk expression. And then this is independent of L squared. Q squared f of x and w. This is a rational function with such that f of x and 0 is 0. Okay. Keep in mind the structure. I don't know where the erase is. We want to repetitively use Feynman parameters, and for Feynman parameters, what we need is something. Something. So there's an integral over some variable p or L or something p plus something or minus something, right? We're gonna repackage everything always in this form. All right, so this R of x and w is just something that is a function of this x and w and the external momenta. Plugging everything in there and doing the integral, I'm not gonna bother you with it anymore. I'm just gonna give you the answer. It becomes this, I lambda r squared, of course. This is the epsilon dependence. That's going to be very essential for us, right? There's an integral over dx, dw, 1 over this horrible thing, r to the power 1 minus epsilon, w to the power minus epsilon over 2. We might not be able to do this integral, but we can't care less, because all we want is we want to see the epsilon going to 0 piece. So all we need to worry about are the divergences as epsilon goes to 0. This term becomes singular, right, at epsilon going to 0, but there's another divergence here. The other divergence has to do with comes from this term when w goes to 0. Keeping track of this, extracting the pole and all that, you end up with an expression of this type, minus I lambda r squared over lambda r over 16 pi squared, mr squared over 3, 1 over epsilon 2. So this is the 1 over epsilon 2 term. I won't, you'll go through this type of calculations in your homework at some point. Good? Yeah.
The 1 over epsilon 2 is expected because it's 2 looping.
Yeah, absolutely. Good. So what counter terms do we have to cancel this term? Now is where the thing that you were saying comes in. So there is this counter term, right? And then there is this counter term. This is the 2-point function at 2 loop counter term, right? This is precise. I erased it, but this is precisely the term that you were talking about, right? Good. So these are the counter terms. How do they look like? So this is gonna look like delta lambda 1 half k1 of mr squared. Why k1 of mr squared? Because this is just literally the integral, the diagram we did before with this bit added to it, right? There's really no difference. And then this guy is just like, you read it off, so it's like a vertex, right? You just read it off and put it in here. Good. So as a homework problem for you guys, you see that these guys, the divergences we found above, and this divergences, they cancel in dim reg, and everything is fine. So this diagram is clean and nice. There are more vertices at two loop. So there is this vertex, which corrects the 4-point interaction. Its corresponding counter term is this, right? So there are all sorts of things. You could just draw all sorts of things and have fun with it. Good. This is all I was going to say for two loops. Any questions?
That diagram is, like the original diagram is under lambda squared, like the counter
This?
terms,
Yeah,
that's under lambda squared.
of course.
Counter terms are, the first one is this under lambda.
No. There is a no. So recall. Okay. How did we cancel this divergence? We canceled it using this. So this is order lambda.
Okay.
Yeah, you wanna, it's, yeah. Any other questions?
How do you effectively keep all the diagrams?
Okay, it's an extremely hard problem. And people have written codes for this, but if you go to a couple of loops, like 5, 6 or something, already you're counting diagrams in billions. I mean, this is a question of growth of, it's just like these are combinatorics, right? So the numbers grow insanely fast, which would imply you're doing billions of integrals, right? This is the origin of a lot of recent work has been, so this tells you that perturbation theory, as we've set it up, is silly, untractable in a sense. It's calculational too hard, right? So what people have been thinking about in the recent times is that in the theories that we're interested in, often there are more symmetries. And these symmetries should be intelligently put in. So right now I told you about word identities, right? But I didn't tell you how to use it. I just checked that. I proved it. And I told you, oh, look, it works, right? But there has to be a way. Every symmetry you have, right, has a consequence that relates these divergences. So you want to intelligently use the symmetries to cut down the number of integrals you do. This is a very important line of research that has led to, well, there are like reasons to believe that at least in some cases, it leads to a reformulation of quantum field theory or other approaches to quantum field. Yeah, but it's a really annoying problem. Yeah. Any other questions? These integrals are not easy, as you've seen, right? Okay, so this is the end of the part 1 of today's lecture. What did we do in summary? In summary, we just worked out a bunch of examples of the, 5-4 theory, the propagator, and the vertex. We looked at a couple of diagrams. We looked at the 1 pi, a 2-loop propagator, right? And 2.1 pi, right? That's a propagator. And we saw there were 2 diagrams. We discussed them both, and we saw that 1 over epsilon squared is the level of divergence in lambda. In momentum cutoff, it was lambda squared, log lambda squared, right? So that was the story. It cancels off nicely. It's all neat. And then the vertex are all sorts of other terms. We did not go through them, but basically it works out. But yeah, at least I gave you a bunch of tools, right? KN, and package these things in the way that we're packaging them. And then we saw that as we're just discussed earlier, these deltas, right, have an expansion in lambda, loop expansion of their own. Good. All right, we're gonna switch gears and talk about effective actions. I'll try to, this is a fascinating topic, and I'll try to, which belongs to non-perturbative methods, quantum field theory. So what we're gonna discuss for a couple of, for this lecture and the next lecture, and perhaps part of the RG flow business, it's going to be fully non-perturbative. So at first, in my head, I wanted to postpone all of these non-perturbative discussions for later. But to part 2 of the course, I don't think that makes much sense. So we're gonna discuss it now. Let me try to motivate it in several different ways. Why? So what we are gonna introduce is a quantity called effective action. And it's a deserving name. I'll describe it why it's called an action and why is it called effective action. And it's very, this structure, what we're gonna use is gonna help you. It's very connected to statistical mechanics. It's very connected to classical physics. It's basically Legendre transform. But it includes a lot of beautiful physics in it. So recall what action was. Going back to lecture 2-3 of part 1 of the course, action was a local functional, which meant that you could write as an integral over space-time of a Lagrangian density that's extremized on the solutions to the equations of motion. So you take this, the raison d'etre of this functional was you take it, you vary it with respect to the function, the field, and on the solutions to the classical equations of motion, this vanishes. This equation gives you the equation of motion. All right, so we talked a little bit about Schrödinger-Dyson and how this like the quantum version of classical equations of motion. But let's try to. I said that's not really tractable. It is related to what I'm going to say, but let's just try to approach it a little bit differently. So in quantum world, phi of x, the classical field becomes an operator distribution, right? Phi hat of x. Now, the way to go back to something classical, to a function, instead of an operator, is just to calculate the expectation value, right? We can, now that's a classical function, that's phi classical of x. Now, you might complain, rightly so, that in all the theories we were discussing, we're looking at vacuum correlation functions, and the 1-point function in the vacuum would vanish, right? It would just like A and A dagger kill you know, A kills the vacuum, A dagger doesn't kill the vacuum, but it will kill the other side, the abroad. But that's only true in the vacuum. Quantum field theory has a lot more states in it, right? So actually in physics, if I want to do physics, if I want to study quantum field theory, I might be in a setup where there is a non-zero classical value for the quantum fields in our universe, right? We have like we're living in the background of the Higgs field. So we want to generalize our discussion to the cases when the 1-point functions are not zero, right? So when they are not zero, what are they? It's just a function, right? That I'm going to call phi classical of x. Now, remember, notice that this is the result of a quantum calculation, right? I have to do a path integral, insert a field in there, do the path integral to read this off. But now my question is this. The same way that I found the classical solution, the solution to classical equations of motion by varying action Lagrangian, is there some action functional of phi classical whose variation gives me the quantum answer, right? So I want to write down a functional, right, whose variation gives me the 1-point functions of the quantum theory, non-perturbative. So this functional, whatever it is, it will include, if in perturbation theory, all loop, all quantum corrections, right? Because it's repackaging for your quantum calculation. The answer to that is going to be effective action. Now, the meaning of effective is pretty clear, hopefully. It looks like an action, looks like a classical action because it's a functional of a normal functional, but this variation gives you the 1-point function, right? Full quantum 1-point function. Good. So how are we going to define such a functional? So that is the motivation. That's what we want, right? Let's do a little bit of detour to statistical field theory. This is classical fine temperature physics, all right? So I'm gonna tell you that you already know about effective actions. You've already done this before. Consider classical Ising model, where there are Ising variables S plus minus 1. They take values plus minus 1. For example, you can have nearest neighbor interactions, on-site terms to Hamiltonian, and this is the Hamiltonian, right? In fine temperature, I have to calculate the partition function. That's the moment generating functional. It's a sum over all microstates, right? Of e to minus beta h of the microstate. Microstate means some combination, it's a sequence of zeros and ones, and I have plenty of them. How many of them do I have? 2 to the power of n, right? All right, so each microstate is like that. This is the sum I'm going to try to do. This already looks like the quantum path integral we've been doing. We'll see that in a sec. So let's say I'm in the continuum limit. So first, let's try to think about. I'm gonna actually explain the continuum limit. Maybe I did this before. I don't recall, but let me try to do it again. Let's say I have a lot of these guys, and I'm gonna look at very low energies. I'm gonna coarse grain them. How do I coarse grain them? I box a bunch of these guys, for example, these 4, and take the average of them and give that average a name. We already give that a name. That's sort of like that's like effective spin, right? But it's magnetization. That's what magnetization is. It's the average it's the sum of these spins in each block, and I just go along. Now, after one step of this resummation, your partition function is a sum over all configurations of magnetization, right? And then there's a second sum, which sums over all microstates of a particular magnetization. So I split it into the double sum. Good? This part of the sum I can do and write it as e to minus beta h of m. So I'm done with my coarse graining. I wrote my partition function in terms of these new degrees of freedom by partially performing this sum over like some microscopic degrees of freedom. This is the meaning of coarse graining. In physics, if you ever see it, many body physics, this is literally what it is. I'm gonna recycle this stuff when we get to the normalization group as well. All right. The thing that you notice here is that SIs were variable between 1 and 0. This magnetization for force spin takes values from 1 to minus 1, but also values in between. As I look at very, very low energies, as I block more and more things or repeatedly do this, in one block, I have many, many spins. So my magnetization basically becomes a continuous variable that takes values from minus 1 to 1, with the vast majority of states averaging to 0, right? So my m of these blocks becomes in the continuum limit m of x, where x as the block index becomes continuous, and so does m. So it becomes a field. My partition function becomes a path integral over the magnetization field e to minus m. This is statistical field. This is basically the same thing as what we've been doing for the generating functional quantum field theory, right? In Euclidean, if you do the weak rotation, this is identical to that, right? But remember, this is classical physics. Over there, we had quantum physics. How do you go between the two? Here, there are thermal fluctuations, right? What is the perturbation theory you want to organize here? What is the perturbation theory? Anyone has an idea? Remember the origin of the perturbation theory in the path integral quantum field theory path integral. What are the loops in? H bar. You had the action e to the power of I s over h bar. H bar is small. You do the saddle point approximation. and expansion. If you want to do the similar thing, what is the parameter that you have to take to be small or large?
Temperature.
Yeah, you have to work with temperature. All right, so you could, and the temperatures control the size of the fluctuations. The same way that H bar controls the size of the quantum fluctuations. So the analogy is thermal fluctuation, quantum fluctuations, right? All right, very good. Very good. Now, we did something over there in thermal physics that hopefully we recall. You take the partition function of this magnetic field, you want to study it. Of course, the partition function as we wrote is kind of boring. You want to put this set of magnets in a magnetic field. So you want to add to your Hamiltonian a term that's an external field that will just make these guys align in a particular direction. So that is your term after coarse graining. It's an integral of b of x m of x. This is your partition function of b. This b of x in quantum field theory was our j. It's the external source. And giving it a magnetization, this was field phi, and giving it a magnetization is like giving it a 1-point function, right? Which was phi classical. All right. So here, what did we do? What did we use this for? We constructed, well, we took the log of z of b minus 1 over beta. This is the Helmholtz free energy. The same way that this guy generates a partition function, this guy generates the connected correlators. Sorry, this partition function generates the correlator, this generates the connected correlators. Now, if you take f of b and take derivatives with respect to b, with a minus sign, the derivative will bring down integral of x mx. So the 1-point function of integral of mx dx, which is called average magnetization, is just the derivative of f with respect to b at fixed temperature with a minus sign. All right. What did we do? Why do we do this? Because we wanted to calculate m of b, magnetization, as a function of external field. This is saying that I have this material, I'm going to have some huge magnets here, or some magnetic field. I'm going to apply this magnetic field to it, and I want to know under this magnetic field, what is the response of my material? What's the average magnetic field, average magnetization I get due to the external field that I apply? All right. Is this part clear? The next step is is a little bit subtle. All right. So far I haven't done anything. It's all familiar. The next step is this. If you know the response of the function, m, magnetization as a function of the external magnetic field, could invert this and solve for the external magnetic field given the magnetization. So if you know m as a function of b, you could also view it as b as a function of m. What external field is required to get a particular magnetization? The analogy holds identically in quantum field theory. In quantum field theory, if you want to calculate correlation functions, right, you start with z of j. You take derivatives with respect to j, and it gives you the 1-point function. So what you solve is you find the 1-point function as a function of the source. You find phi classical as a function of the source. Inverting this would mean that you want to write down j as a function of phi classical. This is going to be our effective action. We'll see, related to our effective action. So we already found the function of phi classical, so that's good. Right? Now, why is it going to be our effective action? That's because of the nature of the construction. So we'll see. So the question here is there a function? So we saw that, so m of b is the magnet. So sorry, f of b is a function whose extremization gives you m. Now here the question is there a function of m whose extremization gives you b? Right? That function is called the Gibbs free energy. This is the Legendre transform of Helmholtz free energy. You just take your Helmholtz free energy plus magnetization mb. You take derivative of this g with respect to m, and you find B. This is Legendre transform. We do this in classical physics as well. Lagrangian and Hamiltonian are Legendre transform of each other. How does that work? So Lagrangian viewed as a function of Q dot, right? That is like f of B, right? It's a function of B. If you take Lagrangian, vary with respect to Q dot, you get P. That's the very definition of canonical momentum, conjugate momentum, right? So del F, del B gives you M. This is like M. MB, which is PQ dot, plus, in this case, minus Lagrangian is the Hamiltonian. It's a function of P, not Q dot, whose derivative with respect to P gives you Q dot. Right? So, and Legendre transform, in the case of classical physics, with Legendre transform between Q dot and P. In statistical physics, we Legendre transform between B and magnetization, external field and magnetization. Right? So the example of quantum field theory that we're going to discuss is like this, like statistical field theory. Is this part clear? I'm running really behind. All right, good. So effective actions in quantum field theory. In Euclidean signature, the generating function of quantum field theory is this. Z of j is the path integral over phi, e to minus L minus d of x, d of x, the Euclidean Lagrangian. Hopefully you recall that Euclidean Lagrangian was a little bit tricky. Plus integral of d of x, j of x, phi of x, right? This, we said that this is the generating function for correlations. Functions, the e to minus w of j, this is like the free energy kind of thing. That's the generating function for connective correlation functions. In particular, minus del w del j is phi classical, right? The 1-point function. Good. Actually, let me remove this because that's incorrect. All right. So what follows is that, let's see actually how am I going to deal with this in this short amount of time, because a bit all right, let me just try to get a little bit further. This equation, this equation gives us phi classical as a function of j. The same way that we found magnetization as a function of the external field, right? It's a response thing. External field is what you control, and you want to see what the property, how the properties change. So phi of classical, it's not a response, because certain response is reserved for something else in physics. But it's like, yeah, you know what I mean. Now, inverting this is like j as a function of phi classical. This is the analog of Gibbs free energy, is called effective action, and it's the Legendre transform of W of j, the Helmholtz free energy. Analog of Helmholtz free energy. What is the Legendre transform? Well, it's pretty straightforward. W of j plus integral of d4 j of x, phi classical of x. This is your very definition. So it's like Gibbs effective action. Effective action is like Gibbs free energy. The property of it is that if you take this guy, effective action, and vary with respect to phi classical, it gives you j of x. If the source is 0, this variation is extremized on phi classical. So solving this equation, if you know j of x, will tell you what your 1-point function is. So it's a functional like action that's extremized, but includes the contributions to all quantum effects. Remember that this equation looks classical, but it packages all like this. There's a path integral with some operator inserted in it, right? To all orders in perturbation theory. Well, this is just a redefinition. I haven't done any magic here. All right. Okay, so let me just say this, and the remainder will stop. We'll stop after. It's important that this effective action is a local functional. Locality is a key principle for us, right? So that already means that I can write this down as an integral over something that I'm going to call effective potential, right? The same way that we have Lagrangian density, I have effective potential. That's what we often work with. Effective potential. Now, let me just end this discussion with this. Z of j is the generating function for correlation functions. I said this several times. W of j is the generating function of connected correlation functions. This effective action we defined, it's Legendre transform. Not only it gives you the 1-point function, but also it's the generating function for one PI diagrams. What is a 2PI? Oh, sorry, the one point function, 1PI, you know what it is, right? What's a 2-point function, 1PI? The 1PI propagator Fourier transform. What's a 3-point function, 1PI? The Fourier transform of the 1PI 3-point function, a 3 vertex. What's a 4-point function? 4 legs, well, n-point function, 1PI. N-point function, 1PI after Fourier transform is n legs, 1PI, the ongoing. Right? So not only it gives you the 1-point function, it gives you these guys. Unfortunately, we ran out of time, so we won't have time to go through the proof of this. Actually, I'll not prove the grand thing, but I'll prove to you guys that it gives you a 2-point function, the 3-point function, 4-point function. The rest you'll maybe yeah, we'll see. All right, so let me summarize and pause for questions. Actually, are there questions before I summarize?
I think the view of Platons is each classical solution.
Sorry, say it again.
So phi CL is classical solution.
Yes.
Then you remove that phrase.
Oh. It is the classical. It is the thing, but I just didn't want to. Yeah. Yeah. I don't want to get it confused with spontaneous symmetry breaking and things that we're gonna say later. Yeah. Any questions? Other questions?
Yeah, a little bit before this, when we said, like, okay, we can set J to 0 and then it's extreme.
Sorry, one second. No, the answer to that technically is incorrect. It's what I had there is incorrect. The 1-point function in full generality has all sorts of quantum corrections. It's not by classical. In full generality, in like a crazy trap. Yeah, sorry.
So when we said, okay, we can set J to 0 and then we'll get this B classical that's extremized on the effective action. But is there anything different in the path interval we're doing that won't just give us the background expectation again, which is 0? Like, are we not doing the whole projecting onto the vacuum thing anymore? They say like we find like we
So,
compute W.
Okay, let's rewind. What we did was we defined the path interval. Then we solved the path interval for a free Gaussian theory. We realized that it's a bunch of harmonic oscillators, therefore all the odd point functions are 0. That's what we did. Here, I'm nowhere saying anything about what the Hamiltonian interaction is. So it has nothing to do with the Gaussian fixed point. Could be crazy, wacky, whatever. Right? And yeah.
Okay.
This is a fully non-perturbative thing. Good. Any other questions? Of course, in perturbation theory, the 1-point functions are just gonna vanish. The hard point functions won't, right? Like, so this is, here's the point, The one, like, okay, in perturbation theory, this is not necessarily teaching you something crazy about the 1-point function, but because it gives you the 1PI, this is super helpful thing. Because 1PI, we're just doing, well, it repackages that. There's no winning. Like, in a sense, if you see the calc, so what people do is, let's say you want to solve a theory at some certain number of loops. What you do is you renormalize the theory. You go through all these diagrams and all this insanity, And then to repackage everything such that in the future, people can use it nicely, you construct effective action at that loop. Right? That's what you do. And now people don't need to worry about your diagrams, find the diagram in your like crazy long papers, right? They just take the effective action and they know how to calculate these 1PIs by taking derivatives. That is part of the reason that we sort of think that maybe this like insane number of integrals we are doing is unnecessary. But anyway, good. Any other questions? Okay, so if not, let me just summarize. Yeah, this is a little bit involved. So in summary, what did we do? In the beginning of this course, this lecture, we talked about two loop diagrams. We talked about the structure of divergences. We saw that you get terms that are like in 4 dimensions. By the way, a lot of what I said, you saw the dimension count. I just put 4 in there. So we took lambda phi 4 and 4D, and we see divergences in the propagator at 2 loop, 2 bubbles on top of each other. They were lambda squared log lambda squared, right? Then we said that n loop, you're gonna get terms that are higher powers of log lambda squared, the whole thing, 2 higher powers, right? And in normalized perturbation theory, we should make sure all of these guys cancel, right? Now there is this formal theorem that ensures that's going to happen, but we saw that explicitly by doing these calculations, right? I introduced a bunch of tricks, K1, K2, Kns. These are like a good way of reorganizing your integrals, so that the goal is that you write the n loop in terms of n minus 1 kind of quantity, renormalized quantities, and the cancellation of those implies cancellation of these, right? That's the structure that we saw. One important point was that when in the vertices that we introduced in the cross in the counter terms, all those are functions of lambda, so they admit a lambda expansion, right? As you go to higher loops, there might be higher order contributions, right? As we saw in the case of this guy. Okay. For the scalar. And the same logic applies to QED at 2 loop, whatever theory you want to higher loops. There are more confusing things at higher loops, but yeah. Also, these perturbation theories are asymptotic. You guys know what that means?
Like it converges after a certain level, then diverges.
Yeah. So if you could calculate them to 250 loops, you would be wasting electricity and your resources and your life. Because most of the time, these guys, as you calculate, like higher order lambda terms, they are giving you the answer with more precision, and at some point they start growing again. So you're producing junk, right? And that's a very well known, that's an asymptotic perturbation series. And that's a well-known story. There's some beautiful physics associated with that. And it's because you're expanding around the wrong saddle, or a saddle, instead of fully non-perturbative effects. There's a long story. It's a very active area of research. Resurgence is called. So perturbation theory at higher loops secretly knows about other vacuum of the theory. Anyway, all right. So then that was the end of the discussion for 2 loops. Then we switched gears and we said we're going to talk a little bit about background field methods. Hopefully it's clear why I call them background field methods, because it's like background magnetic field that you apply. There's background J that you apply to see the response of your partition function. So far we're looking at vacuum correlation functions. So we're taking derivatives and setting J equals 0. In this whole story, I was not setting J equals 0, right? I was sourcing it. What I'm gonna do, and then what we saw, we defined this effective action. It's a functional, it's a classical thing, right? It's a functional of the 1-point function phi classical, full quantum 1. But variation with respect to phi classical gives you J. Higher, so if you go take higher derivatives of it, it will give you, I promise, argue for you, it gives you the 1PI diagrams. So it's like, as I said, once you do these calculations to a certain loop and normalize the theory and all that, you're hopefully going to present the whole thing the nicest form as an effective action. Yeah, so it's like Legendre transform. It's the same thing that we do for going from Hamiltonian and Lagrangian is the same thing we do with magnetization. And gives free Helmholtz free energy and gives free energy. What I'm gonna do in the next lecture is I'm gonna argue for you guys that the variation of this guy, this is generating function for 1PI diagrams. And also, we're gonna discuss QED in a background field. So that's going to be important. All right. Any questions? Yeah.
So when we talk about the perturbation theory being asymptotic, is it known for, say, like QED when this happens? Like when you should stop?
Oh, yeah.
Is it a lot loops or?
No. I think we'll get, I think I'll discuss that. I think. So if not, just read up on Landau poles and. Landau poles, that's it. All right, any other questions? I should know if off the top of my head, sorry, I do not. Yeah.
No, question of terminology. Why do you call the effective potential, not something like effective Lagrangian? Maybe reason.
Because other people call that. I don't know. I really don't know. Maybe some people call it effective. No. Effective Lagrangian is kept for some. Yeah, effective Lagrangians are usually Lagrangians that are effective field theories, which is something else. So here we have sort of integrated all the quantum stuff, right? We've integrated all the quantum stuff. Over there in effective Lagrangians, you have integrated only the quantum UV part, the UV quantum part. Here you have done all the integrals. All right, any last questions? Okay, if not, have a nice day, guys.